Hello everyone, and welcome to our course on kinematics, the branch of mechanics that describes motion from a purely geometrical point of view. In this chapter, we will explore how objects move without discussing the forces that produce that motion. Our focus will be on describing motion accurately using mathematics and geometry. We will begin with the simplest type of motion, called rectilinear motion, where an object moves along a straight line. You can see a particle moving along a curved trajectory. The black curve represents the trajectory, which is the path followed by the particle during its motion. At one particular instant, the particle occupies a specific position on this trajectory. From this point, two important vectors are drawn. The blue vector, labeled v, represents the velocity of the particle. Notice that the velocity vector is tangent to the trajectory. This means that velocity always points in the direction of motion. The red vector, labeled a, represents the acceleration. Unlike velocity, acceleration does not necessarily point in the same direction. It describes how the velocity changes with time, either by changing its magnitude, its direction, or both. Four fundamental quantities are introduced. The first is position, or displacement, represented by r, x, or s, depending on the coordinate system. The second is velocity, represented by the symbol, versus the third is acceleration, represented by a. Finally, we have time, represented by the symbol t. They form the foundation of kinematics. Throughout this course, we will learn how these quantities are related mathematically through calculus and how they allow us to predict and describe the motion of any particle. Every moving particle continuously changes its position with time. If we know the position of a particle as a function of time, we can determine every other quantity that describes its motion. Let us begin with the position vector, denoted by r. The position vector specifies the exact location of the particle at any instant. Because the particle moves, its position changes continuously. Therefore, we write the position vector as a function of time, r equals r of t. The next quantity is velocity. Velocity tells us how rapidly the position changes. Mathematically, velocity is obtained by taking the first derivative of the position vector with respect to time. We write v equals dr over dt. The derivative measures the instantaneous rate of change. In other words, it tells us how fast the particle is moving and in which direction at a particular instant. We now move one step further. If the velocity itself changes with time, the particle experiences acceleration. Acceleration is defined as the derivative of the velocity with respect to time. Mathematically, v equals dv over dt. Since velocity is already the derivative of position, acceleration can also be written as the second derivative of the position vector. Therefore, v equals d squared r over dt squared. This relationship is one of the most important equations in mechanics. It shows that every quantity in kinematics originates from the position function. Position gives us velocity. Velocity gives us acceleration. Throughout this course, we will repeatedly use these three equations to analyze different types of motion. They form the mathematical foundation of classical mechanics. We now consider the simplest possible motion in physics. This type of motion is called one-dimensional rectilinear motion. As the name suggests, the particle moves along a single straight line. That straight line is represented by the x-axis. Because the motion occurs in only one dimension, we no longer need three coordinates. A single coordinate, x, is sufficient to describe the particle's position. At any instant, the particle occupies a point located at coordinate x. As time passes, this coordinate changes continuously. Therefore, we write x equals x of t. This expression tells us that the position depends on time. If the particle moves toward the positive direction of the axis, the coordinate x increases. If it moves toward the negative direction, the coordinate decreases. Notice that motion in one dimension is much easier to analyze than motion in two or three dimensions. Nevertheless, the same physical principles remain valid. Position still describes location. Velocity still describes the rate of change of position. Acceleration still describes the rate of change of velocity. Studying one-dimensional motion allows us to understand these concepts before extending them to more complicated situations. Let us now examine how velocity is defined mathematically. Imagine that a particle moves from an initial position x1 to a final position x2 during a time interval extending from t1 to t2. The particle has therefore undergone a displacement equal to delta x equals x2 minus x1. The corresponding time interval is delta t equals t2 minus t1. The ratio between these two quantities gives the average velocity. We write, average velocity equals delta x divided by delta t. Average velocity tells us how much the position changes during the entire time interval. However, many motions are not uniform. The velocity may change from one instant to another. Therefore, average velocity cannot describe the motion precisely at every moment. To determine the velocity at one exact instant, we gradually reduce the time interval. As delta t approaches zero, the average velocity approaches a limiting value. This limiting value is called the instantaneous velocity. Mathematically, v equals the limit of delta x divided by delta t as delta t approaches zero. Using differential calculus, this expression becomes v equals dx over dt. This equation is one of the cornerstones of kinematics. It tells us that the velocity is simply the slope of the position versus time curve. A steep slope indicates a high velocity. A horizontal slope indicates that the particle is at rest. A negative slope indicates motion in the negative direction. By interpreting the graph in this way, we can immediately understand the motion of the particle. In the previous slide, we learned that velocity describes how quickly the position of a particle changes with time. However, in many real-world situations, velocity is not constant. A car leaving a traffic light gradually increases its speed. An airplane accelerates along the runway before takeoff. A cyclist slows down while climbing a hill. In all these situations, the velocity changes with time. The physical quantity that describes this change is called acceleration. Average acceleration is defined as the change in velocity divided by the corresponding time interval. Mathematically, we write, average acceleration equals delta v divided by delta t. If we want the acceleration at one precise instant, we allow the time interval to become infinitely small. This leads to the definition of instantaneous acceleration. Using calculus, we obtain, acceleration equals dv over dt. Since velocity is the derivative of position, acceleration can also be written as acceleration equals the second derivative of position with respect to time. This equation tells us that acceleration measures how rapidly the velocity changes. It is important to remember that acceleration does not always mean increasing speed. A particle may have acceleration because its speed changes, because its direction changes, or because both change simultaneously. Therefore, acceleration is also a vector quantity. It has both magnitude and direction. Throughout mechanics, acceleration plays a central role because Newton's second law directly relates force to acceleration. In this slide, we discover one of the most powerful ideas in calculus and physics, integration. Imagine observing the particle during an extremely small interval of time. During that tiny interval, the particle travels a very small displacement equal to its velocity multiplied by the small time interval. By adding all these tiny displacements from the initial time to the final time, we obtain the total displacement. This mathematical process is called integration. On a velocity versus time graph, the integral is represented geometrically by the area under the curve. Notice that the region below the time axis, labeled A1, corresponds to negative velocity and therefore contributes a negative displacement. The region above the axis, labeled A2, corresponds to positive velocity and contributes a positive displacement. The total displacement is the algebraic sum of these signed areas. However, if we want the total distance traveled, we ignore the direction and add the absolute values of both areas. Finally, the same principle applies to acceleration. The area under an acceleration time graph gives the change in velocity. These relationships connect geometry, calculus, and physics, allowing us to determine motion directly from graphical representations. One of the most important cases in kinematics is motion with constant acceleration. This means that the acceleration remains the same throughout the motion. Although many real motions involve changing acceleration, constant acceleration provides an excellent approximation in many practical situations. Examples include a freely falling object near the Earth's surface, a car accelerating uniformly, or a train leaving a station. Because the acceleration is constant, we can derive a set of equations known as the kinematic equations. The first equation relates velocity and time. It states that the final velocity equals the initial velocity plus the product of acceleration and time. The second equation gives the position of the particle at any instant. It combines the initial position, the initial velocity, and the effect of constant acceleration. The third equation relates velocity directly to displacement without explicitly involving time. These equations allow engineers and physicists to predict the future motion of a particle using only a few known quantities. We now extend our study from one-dimensional motion to motion in three-dimensional space as known as Cartesian coordinates. Instead of describing the position with a single coordinate, we now use three coordinates, x, y, and z. Together, they define the exact position of the particle at every instant. The position vector is written as the sum of three components along the x, y, and z directions. Although the particle appears to move in a complex three-dimensional path, the motion can actually be viewed as three independent one-dimensional motions occurring simultaneously. Each coordinate changes according to its own function of time. By combining these three independent motions, we obtain the complete trajectory of the particle. If we eliminate the time variable from these equations, we obtain the geometric equation of the trajectory itself. Let us now examine the geometric interpretation of velocity and acceleration in three-dimensional space. Notice the curved trajectory shown on the figure. At every point of this curve, the velocity vector is tangent to the path. This means that velocity always points in the direction in which the particle is moving. Acceleration, however, behaves differently. It is not restricted to the tangent of the trajectory. Instead, acceleration determines how the velocity changes, either by increasing or decreasing its magnitude or by changing its direction. In Cartesian coordinates, acceleration is obtained by taking the second derivative of each position component with respect to time. These three second derivatives form the three components of the acceleration vector. In the previous slides, we described motion using fixed Cartesian coordinates. We now introduce a new coordinate system that moves together with the particle. This system is known as the Frenet frame. The first unit vector is the tangential vector. It is always aligned with the direction of motion. The tangential component of acceleration acts along this direction and changes the speed of the particle. The second unit vector is the normal vector. It points toward the center of curvature of the trajectory. The normal component of acceleration changes only the direction of motion, without affecting the speed. This moving reference frame provides a much more intuitive description of curved motion than the fixed Cartesian system. We have now reached one of the fundamental equations of curvilinear motion. This equation separates acceleration into two completely independent components. The first component is the tangential acceleration. It is equal to the rate of change of speed with time. If this component is positive, the particle speeds up. If it is negative, the particle slows down. The second component is called the normal acceleration. It is directed toward the center of curvature and changes only the direction of motion. Notice that this component depends on the square of the speed and is inversely proportional to the radius of curvature. The faster the particle moves, or the tighter the curve becomes, the greater the normal acceleration. This decomposition allows us to distinguish between two very different physical effects, changing how fast an object moves and changing where it moves. Together, these two components completely describe the acceleration of a particle moving along any curved trajectory. We introduced the polar coordinate system and saw that a particle's position can be described by its radial distance and its angular position. We will now determine the velocity of a particle moving in this coordinate system. Unlike Cartesian coordinates, where the coordinate axes remain fixed, the unit vectors in polar coordinates rotate together with the particle. This means that both the magnitude and the direction of these vectors may change with time. As a result, the velocity has two distinct components. The first component is called the radial velocity. It describes how quickly the distance between the particle and the origin changes. If the particle moves away from the origin, the radial velocity is positive. If it moves toward the origin, the radial velocity is negative. The second component is called the transverse, or tangential velocity. This component is associated with the particle's angular motion. It is proportional to the angular velocity and to the radial distance from the origin. By combining these two components, we obtain the complete velocity vector in polar coordinates. This decomposition provides a much clearer description of curved motion than Cartesian coordinates. It is widely used in orbital mechanics, rotating machines, robotics, and many branches of engineering. Circular motion is one of the most common examples of motion described using polar coordinates. In circular motion, the particle follows a path whose radius remains constant. Although the distance from the center does not change, the direction of the particle changes continuously. For this reason, the velocity vector is always tangent to the circular path. At the same time, the centripetal acceleration always points toward the center of the circle. This inward acceleration is responsible for continuously changing the direction of the velocity. If the particle moves with constant speed, the magnitude of the velocity remains unchanged. However, because its direction changes at every instant, the velocity itself is not constant. Consequently, even uniform circular motion involves acceleration. This is a fundamental concept in mechanics. Whenever the direction of velocity changes, acceleration exists, even if the speed remains constant. Let us review the most important concepts introduced throughout this chapter. Every analysis of motion begins with the position of the particle. Position specifies where the particle is located at a given instant. Taking the first derivative of position with respect to time gives the velocity. Velocity tells us how rapidly the position changes and indicates the direction of motion. Taking the derivative of velocity gives the acceleration. Acceleration measures how rapidly the velocity changes with time. Depending on the type of motion, we may choose different coordinate systems. Cartesian coordinates are generally preferred for rectilinear motion and many two-dimensional problems. Polar coordinates become more convenient whenever curved or circular trajectories are involved. Choosing an appropriate coordinate system often simplifies both the mathematics and the physical interpretation of the problem. These concepts form the mathematical foundation upon which all classical mechanics is built. That's all for today. See you in the next lesson.